Welcome back. This is now, ooh, that smudged badly. This is now part 2 of our video on section 3.5, rational functions. This is our rational function. It is a fraction of polynomials. In part 1 of this video, we found that this was the y-intercept, this was the x-intercept, this was the domain restriction, and this was the end behavior. And now we're going to talk about what those things look like on a graph. Most of these things on a graph are extremely straightforward. These are points. We know about points. These are your x and y intercepts. They haven't changed from all the other x and y intercepts you've ever dealt with throughout the rest of your life, so no surprises there. They're still points. This is a horizontal line. That's the end behavior. We kind of know what that's going to look like already. This is what's going to be weird for us. We have to figure out how to graph a domain restriction for a rational function. And to do that, I'm going to make a table of values so I can explore what happens around that point and see what's going to happen with the graph there. So I'm going to start with the table of values for x and y. I know that 1 is no good. If I try to plug in 1, bad stuff's going to happen. It's not going to work out for me. 1 is not an option. But the interesting thing is, I can't plug in exactly 1, but I can plug in numbers that are really close to 1. So I can start plugging in stuff like 1.1. It's not the domain restriction, but it's real close. It's kind of like this is like the mathematical version of that game that little kids play where they like put their finger right in your face and they're like, I'm not touching you, I'm not touching you. That's this. We're going to get really, really close to 1. We're not going to touch 1, because then we'd get in trouble with the math parents, because we would actually touch it, and we're not allowed. But we're going to get really, really close to it, so that we can say, I'm not touching you, I'm not touching you. It's going to be great. So, when we plug in 1.1, it's going to look like this. Y equals, let's see, that'll be 2.2 plus 6, should be 8.2. The denominator is going to be 1.1 minus 1 should be 0.1. I think that'll give me a 82. Some big numbers here. It's alright. I'm going to try 1.01. I'm going to get 10 times closer and see what happens. This time I'll get y equals, let's see, 2.02 plus 6 should give me 8.02 over 0.01. That'll give me 802. I'm going to get 10 times closer again. This one should give me 2.002 plus 6 should be 8.002 divided by 0.001. I think this will give me the 8,002. And hopefully by now the pattern is pretty clear. Hopefully it's clear enough that if I put in something like 5 zeros and then a 1, you should expect an 8, 5 zeros, and then a 2. So here's what's very interesting about this. This number is very small. This number is almost 1. It is, in fact, what do we got here? Hundreds, thousands. This is 1/10,000th away from the number 1. And the output we're getting from here is 8 million. So you plug in a number that's really close to 1, you get 8 million. You plug in a number that's even closer to 1, you get 80 million. If we did this is 5 zeros. If I did one with 6 zeros, which is just a tiny, 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 tiny bit closer to 1, this thing goes from 8 million to 80 million. These numbers are exploding. They're getting out of control big in an unreasonable hurry. I'm going to try to graph that over here. Just a little part of it. Okay. here's y equals 1. When I put in numbers close to 1, I have to mess with the scale. I'm getting 82, 802, 8 million, or yeah, 8 million up here. And these are all just closer and closer and closer to 1. 1.1 and 8.2 is probably over here somewhere. Yeah. Here's 8 point. This is not to scale. Or, sorry, 82. This is 802. 8,002. This up here would be 8 million and 2. So these numbers, if you start just to the right of 1 and move towards 1, these numbers are getting explosively big. The slope here is basically vertical. So we could do a similar exercise and find out what happens if we plug in numbers on the other side of 1. So I'm going to plug in 0.99, or I'll start with 0.9. 0.9 should give me 1.8, so 7.8 divided by negative 0.1, so negative 78. 0.99 should give me 7.98 divided by 0.01 negative. So this will give me negative 798. I'm guessing that 0.9999, if I use 4 nines, I'm probably going to get negative 79998. If I'm wrong about any of these, I'm kind of just guessing because I'm in a hurry. You can check this on your calculator to see if I'm wrong. You probably should. So again, we have the same pattern occurring where if you plug in numbers close to 1, very, very, very close, the distance between these two numbers is tiny. It's infinitesimal. But when you plug in these numbers that are close to 1, you're getting numbers that are just absurdly large. 800, 80,000. If I did more nines, I could probably get up to 8 million again, like I did over here. I could probably get up to 8 million very easily. And these are all negative. So this is kind of doing the same thing. As you get closer to 1 from the left, this thing is just rocketing downwards at an unreasonably fast pace. So if you look at just this is just the part of the graph that's really, really close to the number 1. If you're looking at just this, you might notice that for the most part, I don't even know if that blue is visible. I'd probably choose poor colors for this. You might notice, anyway, that this looks like a vertical line. Looks like the vertical line x equals 1. This is what pretty much all of these domain restrictions are going to graph like. This is a domain restriction because if you plug in 1, the denominator would be 0, and that's unacceptable. But if you plug in numbers really, 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 really close to 1, the number in the denominator is really, 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 really close to 0. And you can divide by numbers that are really, 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 really close to 0. You can divide by 1/1,000,000th. It's the same as multiplying by 1,000,000. You can divide by 1/1,000,000,000th. It's the same as multiplying by 1,000,000,000. That's why these numbers are getting colossally large so fast. And this will pretty much always happen with these domain restrictions, and it'll give you this behavior that looks like a vertical line. And now it's time to introduce some new vocabulary, because we have this thing that looks like a vertical line, and we have this thing that looks like a horizontal line. So we need a special word for all these lines that this function looks like. The word for this is asymptote. Asymptote is one of my favorite math words, partially because it is one of the most misunderstood math words. Asymptotes feel complicated, they're not that bad. Here's what asymptote means. An asymptote is a line that the function sometimes looks like. That's all an asymptote is. It's just a line that this function sometimes looks like. And you can see that here. This is a vertical, when x equals 1, this is a vertical line that the function sometimes looks like. I mean, it doesn't look like this, when x is other things, like when x is -4 or whatever, it doesn't look like this line. But when x is close to 1, the function looks like a vertical line. Over here, this is the when x is big behavior, this is end behavior. When x is big, the function looks like a horizontal line. So, we call these things asymptotes. This is the horizontal asymptote. This is the vertical asymptote. I guess x equals 1 is the vertical asymptote. X does not equal 1 is the domain restriction. Those things are kind of interchangeable. The domain restrictions you get in terms of x can't equal 1 will turn into vertical asymptotes that look like x does equal 1. It'll be clearer once we start drawing this, which I think we're ready to do. I'm going to sketch myself a graph of this function. Oh, that did not erase as well as I hoped. Oh, I need more on this axis, don't I? Okay, so here's my axes. I'm going to start putting information on this axis. I'm going to start with the point, oh, is this axis? I didn't need to go down further, I needed to go up to 6. 1, 2, 3, 4, 5, 6. Okay, this is my y-intercept, 0, 6. Got it. -3, 0. This is my x-intercept. Got it. Y equals 2 is a horizontal line. I'm going to do one of these. Through 2. X equals 1 is a vertical line. I'm going to do one of these. Through 1. Incidentally, this section is why when you're doing polynomials, I think it's so important that you distinguish between x equals 2 as an x-intercept and the point 2 comma 0 as an x-intercept. I don't like seeing x equals 2 as an x-intercept because when I see x equals 2, I think that it's sort of a vertical line, a vertical asymptote, and I don't want that. Intercepts are points, asymptotes are lines. Points look like this, lines look like this. Don't confuse the two. Anyway, we are ready to graph now. Wait, are we ready to graph? Did I do something wrong? Oh, this isn't positive 6. This is negative 6. It was down there. What am I doing? When x equals 0, this should be negative 6. It's down here. That makes a lot more sense for this graph. Marker's not doing so hot anymore. Okay, time for a quick game of connect the dots. I like to start these from the far ends. Way, 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 way out to the left, I know that it looks like this line. And I know that it picks up this intercept and crosses there, and then it crosses here, and then it goes down. Way, 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 way out to the right, I know it looks like this line. And as it comes in, I know it's going to start to look like this line. That's it, that's the graph. It's the whole thing. This particular clip's running out of time, so I'm going to cut it here, and we'll start the next one in the next vid.